All right, real quick before we begin, is there any questions? Anybody got any homework questions they want to go over? Anything? Do you have a midterm? After the spring break. Oh, yeah. We already leaving? Yeah, we did the first one already. Yeah. Three. Oh, yeah. Plus the final. Yeah. Well, I promise you it's gonna be way easier than the first. Yeah. Remember, I'm dropping the lowest test grade. You guys can go to tutoring, get back half the points that you missed. All right. Yeah. No deadline with getting me back the test. Like when you get it done, you get it done. I understand y'all have busy lives and the tutoring hours are short, so I get it. Yeah. But yeah, any homework questions? Everybody's understanding? All right. Do they have bread? See, Danny, I'm telling you, they had bread. Promise you. Yeah, yeah, yeah. Was about many people. That's good. That's good. I feel like when more people register, like let's say like next time they have it, they might have even more, because they go by how many people register to come, you know. Mhm. St- Stores, yeah. Yeah. Oh, good. Yeah. Yeah. Some of the stuff that they have is like high quality stuff. Like they have grass-fed butter. Like, how expensive that joint is? Grass-fed butter. You know how expensive that joint is? Like, OMG. Like all the other butters are fake, but that one is like OMG, mad expensive. What else have I seen there? The bread is not top quality. I'll admit that. But bread is bread, you know? Um the eggs are okay. They have almond milk, name brand at that. They had Welch's grape juice. I remember that. Like that's Goya. That's name brand right there. Yeah. You know, good. Yeah. Yeah. What else have I seen there that they have? The produce is fire, man. Avocados, peppers, you name it. Did you go? No, I've gone in the past. Yeah. I saw so I keep up with like the Farmer's Almanac, right? So like right now there's like no fruits in season. So like if you see fruits down there, just know that they're not good. You know? Yeah, but there's a couple vegetables in season right now. No. They could. We do have a what you call it, a gardening club on campus. Yeah. Mhm. Nah, they don't. Yeah. hmm We have greenhouses on campus too. So there's one in front of CPH, like the where they have the tutoring. So there's one right there. I feel like that one's broken down, but there might be like half of it might be working. I don't know, something like that. And then behind CPH, where the daycare is another. Yeah, yeah, yeah. Pretty dope daycare, man. Yeah. So like they take from the mayor came 2 weeks ago on Friday. Yeah, Mondani. Yeah, yeah. He was here. Yeah. Yeah, he came to check out the daycare. Yeah. I didn't even know. I found out on Instagram. I'm like, what? I'm like scrolling pictures, like, what? What? Nah. Yeah, I just heard about it on Instagram. Yeah. Um, BCC Cares, something like that. There's a ton of Instagram pages for BCC. Every department got their own page, But this was a daycare one. Yeah. So yeah, he came. But yeah, they take from 6 weeks old. I want to say up to. I'm gonna say first grade because I don't remember what grade, what age first grade is. Yeah, yeah, yeah. But what age is first grade? I forgot. It's five. Okay. Okay, so yeah, yeah. There's a funny bird thing. And then another thing that they do with the daycare, so it's free up until I want to say 2:30, maybe 3:30, something like that. And then after that, it's $5 to keep them for the day. So pretty cool. Yeah. It's past 2:30. In the morning time is free. Yeah. 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 Also like if you're a student and like say you want to study, but you don't want to pick up your child so quickly, you just leave them in a daycare. You can go to the library, do your thing, you come back in the daycare, pick them up. Mhm. It was there. It was the the daycare Instagram. Hold on. Let me see what it is. Also look up your question too. Let me tell you. Yeah, I don't know. Because he's for the students and he wants to put he's putting it all over the Bronx. For people who can't, yeah. We don't really because what it is now. Oh, he wants to do the same thing that we're doing, the 6 weeks old yeah, 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 yeah. They didn't have it? Oh wow. It was like. Well, they didn't have. So yeah, they didn't have it, they moved it out. They
Yeah.
didn't have nothing, they didn't have anything at home. There was an old daycare that was it's kind of off campus. I don't know if you know where I'm talking about now. So like say you're leaving campus like and you're driving off campus, you make the left by the gate. Something like that, but as far as that,
Yeah.
we were, no, we have a daycare, old daycare, but it's a broken down like house right now. I think it's called Alistair House. It's not on campus, but it's near campus. It's across the street. Like when you go down the hill and then you make a right, like you're going towards Fordham, it's that first building on the left, past the library. So like you're leaving campus, going towards Fordham. Yeah. Yeah, yeah, it's a total disaster right now, that building. But that was the daycare years ago, before they built this one over here. Oh, definitely it wasn't there. Yeah. In that big area. Yeah. Yeah. Got you. So it's called BCC Early Childhood Center on Instagram. BCC Early Childhood Center. Yeah, it's pretty good. It's private people do that. Mm-hmm. Yeah. I was gonna do it here, but I didn't, got in my birthplace and I
Yeah.
didn't. I hear you. Yeah, yeah. That's a real picture. Who's there? I don't know if it was was it on the news? It was on the news? Yeah. Yeah. But I knew about it. She told us so. Yeah. I mostly watch Channel 12 News. So I'll see things that'll happen on campus, but like very rarely does news from campus like make it to like the big news stations. But it does happen. When Roscoe Brown died, that made it to all the news stations. That was big. Uh, all right, so what's your question? Hey, you have any questions from homework or anything? It's okay if you don't. I'm just asking. Just reminding y'all this pantry, y'all could go after class, y'all can go tomorrow, you know, bring a cart. If you have a car, bring that. That's better. Hmm. Okay. Wait, what are the 2 points? 1 and 6, just positive like that. Okay, and all they want is a slope, right? So your slope formula, sometimes we write it as m, right? Is equal to the change in y over the change in x, right? Which is just y2 minus y1 over x2 minus x1. Okay? It just asks you for the slope. That's all. Yeah. So now it doesn't matter which point you call x1, y1 or x2, y2. Completely up to you. All right? If you want, we could just go straight forward and call this x1, y1, and then call this x2, y2. Right? After that, just plug in the numbers, right? So y2 we know is 6 minus y1, which is -3, over x2 is 1 minus, right? We have the -2. A little bit of math, right? So we know that the opposite of -3 is +3. So this becomes 6 plus 3. We know that the opposite of -2 is +2. So this will become 1 plus 2, right? This is what? 9 over 3. Call that 3. And that's it. That's how you find the slope. They could also take this question one step further. They could ask you to find the equation of a line, right? So with the equation of a line, that formula is y equals mx plus b. This 3 that you found, that's the m, right? So this would become y equals 3x plus b. Now, to find the b, you just pick either one of these points that you want. It doesn't matter which one, right? You plug that in for x and y, you solve for b, and that's it. I'm gonna pick the first one, 1, 6, right? Just to show you. So this would become the y is 6 and the x is 1, right? Plus b. So this becomes 6 is equal to 3 plus b. Subtract 3, subtract 3. So you know that 3 is equal to b. So rewriting this, if they asked you for an equation of a line that's passing through one of the points given these two points, this would be y equals 3x plus 3. Uh-huh. Mhm. Say it again. What is the like the line? Like, well, so the slope itself is just how slanted the line is, right? This equation right here, the y equals 3x plus 3, that's the equation of the line that's passing through those 2 points. Yeah. It's slanted, so yeah. Point slope formula. Yeah, yeah. I mean, more specifically, this is the equation of a line. Point slope formula is like y minus y1 equals m times x1, no, x minus x1, something like that. Yeah. Yeah. Right. Yeah. Hmm. 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 If you did this one process, it would answer both questions. Yeah. 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 That's gonna be on the test. Yeah. Yeah. It's just this one process does answers like two, three things. Yeah. Got you. Yeah. Right. True, true. So for her question, all they asked for was a slope. So she was done right here. Right. They're gonna ask for the equation of a line. Yeah. Yeah. The 6 is up here from the given points, 1, 6. Yeah. I just chose that point. I could have chose the other point and I would have got the same answer. Yeah. The real reason why I chose that point because it has a one in it, and I know my ones table times table better than my twos and my threes, so that's why. Yeah. Yeah. Okay, no problem. Yeah, go ahead. Yeah, yeah, yeah. Yeah, just watch your video. Yeah, yeah, you can. Yeah, you're welcome. Yeah, I don't have one on me. This thing is locked. Yeah. You're fine. You're fine. Yeah. Um, the tutoring went back to normal. I don't know if I told y'all all that. You know, tutoring is there today as well. Yeah, but remember how like last week I was like, oh, there's tutoring on Sunday and all this. Like, it went back to normal. So there's no Sunday tutoring this week. Yeah, yeah, yeah. Come through. Yeah. Nah, nah. I'm online on Saturday. You know, but to be honest with you, ain't nobody here on Saturday. Yeah, yeah, yeah. Well, there's other tutors here. You know, but one thing that's nice about it, it's not as crowded. You know. Yeah, yeah. I heard stories that in the daytime it gets crowded. I don't see man. But to be honest with you, every time I'm there in the nighttime after class, like it's not crowded. Got you. Yeah. Yeah. I tell you something though. On Tuesday, right? Randomly, like I had like popped up because midterm week, so they needed some extra help in the lab, right? So I was there and it was not crowded at all, even with the snacks, you know. Yeah, yeah. Last week I was there. I didn't tell y'all about it, but it was random. But yeah, like it wasn't crazy packed or nothing. There was more tutors than they were students, you know. Yeah. Yeah. Okay. Yeah, you're welcome. Yeah, but it's pretty chill over there. So I recommend going over there, like do your test corrections, do your homework, you know. Just giving everybody a minute to copy, then we'll switch over. Unless you're done, just let me know. You good? Good. All right. So let's look at what we're gonna get into for today. All right. Different topic. Switching it up. Remix. All right. So we're gonna talk about, hey, so we're gonna talk about some probability rules. We're talking about compound events. Brand new topic. All right. So let's start off with conditional probability and multiplication rules. All right. So let's pretend that we in Vegas, right? We all going after class, right? I mean after the semester, like in May. I'm not talking about like today, right? So let's say you roll two dice, right? What is the probability that you will get a five on each die, right? Consider a collection of six balls identical in every way except in color, right? There are three green balls, two blue balls, one red ball. You draw two balls, right, at random from a collection without replacing the first ball before drawing the second ball. What is the probability that both of those balls will be green? That's kind of like this is what we're going to get into, these kinds of questions, right? So it seems that these problems are nearly alike. They are alike in the sense that in each case, you want to find a probability of two events occurring together. The key word there is together, right? In the first problem, you're trying to find the probability of rolling a five on one die and rolling a five on the second die, right? In the second problem, you want to know what's the probability of drawing a green ball on the first draw and a green ball on the second draw, right? Together, right? That's the key word. So the two problems differ in one important aspect, however. In the dice problem, the outcome of a five on the first die does not have any effect on the probability of getting a five on the second die because these events are independent, right? What happens on one doesn't affect the other, all right? So let's talk about independence. So two events are independent if the occurrence or non-occurrence of one event does not change the probability that the other event will occur, right? I'm rolling the two dice at the same time. If one die lands on three and the other one lands on five, they didn't affect each other. One die is there, one die is over there. You know, kind of like Jumanji. I don't know if y'all ever seen that movie. I'm not talking about the Dwayne Johnson one. I'm talking about the original one, right? Like when he rolled the die at the end, and then one die just like ran off the whole game when it went all the way into like the basement or something. You know, kind of like that. Mhm. All right, so in the problem concerning a collection of colored balls, let's talk about that. The probability that the first ball is green is 3 out of 6, right? Because there's three green balls out of the total six balls that are in the bag or whatever, the urn, right? So since there are six balls in the collection and three of them are green, if you get a green ball on the first draw, the probability of getting a green ball on the second draw is only 2 out of 5. Because remember I took it out, right? So man, I took it out, but I never put it back, right? I'm just going back in the bag and drawing a second ball at random. All right. So, um, 2 out of 5 because one ball has been drawn and only five balls remain. Therefore, the two events in the ball drawing problem are not independent. They are, in fact, dependent, since the outcome of the first draw changes the probability of getting a green ball on the second draw. Right. So that's an example of how two events could be dependent. All right. So let's talk about this. So why does independence or dependence of these two events matter? The type of events determine the way we compute the probability of the two events happening together. If two events A and B are independent, then we use the formula for, right, which I'm going to show you guys, to compute the probability of event A and B. Keyword there, and A and D, right? Remember that word. Okay. So let's look at the multiplication rule for independent events. So the probability of A and B is equal to the probability of A times the probability of B, right? Very simple. What's the key word there? No, and, right? A and D. That's it. That little word. All right. This is on your formula sheet, so you don't have to memorize it. This is in chapter 5 on your formula sheet. Okay. So if the events are dependent, then we must take into account the changes in the probability of one event caused by the occurrence of the other event. The notation A given B denotes the probability that event A will occur given that event B has occurred. This is called a conditional probability. So we read the probability of A given B as probability of A given B. If A and B are dependent events, then the probability of A does not equal the probability of A given B because the occurrence of B has changed the probability that event A will occur. A standard notation for probability of A given B is probability of A slash B, right? Me personally, I don't read it as slash, I read it as given, right? It means the same thing to me. All right. So let's talk about the general multiplication rule for any event. All right. Notice that I just showed you guys three different formulas now, right? So we had this one up here, probability A and B is equal to probability A times probability B. Then we have this one on the bottom. General multiplication for any event, probability A and B is equal to probability A times probability B given A. If you have to memorize something or you want to memorize something, memorize this to get the top one, right? This works for all AND questions, all right? All of them, right? Hmm? Yeah, with the cards. Yeah, yeah, that's this. Yeah. So that's the or. We're gonna get to that. I didn't get to that yet. But yeah, we're gonna get to that. Yeah. The answer of both. Exactly. Exactly. Right? So you can also switch these around. You could say probability of A and B is also equal to probability of B times probability of A given B. That's another way of doing it as well. All right. They both equal the same thing. You know, you can have fun with that. So we will use either formula 5 or 6. 5 is that one, 6 is that one. Right. So this is 5 and this is 6, right? So we will use formula 5 or formula 6 according to the information available. Formulas 4, 5, and 6 constitute the multiplication rules of probability. They help us compute the probability of events happening together when the sample space is too large for convenient reference or when it is not completely known, right? So note, for conditional probability, observe that the multiplication rule is probability A and B is equal to probability of B times probability A given B can be solved for the probability of A given B, leading to the conditional probability formula. So the probability of A given B is equal to the probability A and B divided by the probability of B. Here's what I want you to remember. All right. Whatever comes after the given, right? Remember the slash means given, right? Whatever comes after the given is what's going to be in the denominator. Whatever comes after the given is that's what's going to be in the denominator, right? All right. Let's see if y'all paying attention. Let's switch it up. Probability of B given A. What's that formula? Tell me. What's the numerator going to be? I know. So the top part. What's the top part going to be? It's going to be probability of A and B. Very good. What's the denominator going to be? Probability of. Hallelujah. How did you know it was probability of A? That's amazing. Whatever comes after the given is the one that's going to be in the denominator, right? Whatever the slash is, whatever comes after that, that's what's going to be in the denominator. Mhm. B given A. Yeah, right. That's what the first one is. All right. Any questions on this? It's cool, right? It's on your formula sheet, so you don't need to memorize it. And I know that you all know how to solve literal equations. That's what we did yesterday, right? So if all you had was this formula right here, 5 and 6, I know you know how to solve for that. All right. We did it yesterday. All right. So let's look at an example. Oh yeah. Y'all gonna see my gambling come out now, right? I'll be into Monopoly. I'll be into crabs and all that. I know some of y'all not old enough to go to casino yet, but One day when y'all get old enough, though, it's fun. Yeah. All right. So suppose you're gonna throw two fair dice, right? Oh my God. Let me say another thing too, real quick, right? This word right here, fair, right? Do not play this game on Fordham. I know some of y'all go down Fordham Road. Do not play this on Fordham. Them dice is not fair. All right. They weigh the dice so that one side comes up on top of the other. All right. If you want to play it, go to the casino, right? Where it's fair. All right. Anyway, suppose you're gonna roll two fair dice, right? What is the probability of getting a five on each dice? All right. Like let's actually do it out. All right. So what is the probability of a five on die one? Let's just spell it out. That's supposed to be an equal sign. There we go. So what's the probability of me getting a five on die one? Right? How many sides have five? One out of six. Very good. Right? Because one side of the die has five, and there's six sides of the dice on a die, right? All right. This is a hard question now, right? We gonna get to that part. We gonna get to that part. But this is a hard question now. This is the second hard question, right? So what's the probability of getting a five on die number two? I mean, same thing, right? Because there's six sides to a die and only one side has five. All right. All right. Let's put it together now. Let's put it together. All right. What's the probability of five on die one and five on die two? Exactly. How'd you get that? Very good. All right. You just multiply these together. One over six times one over six. Right? So this is our answer, 1 over 36. Does that make sense? All right. Any questions on this? No? Okay. I know you over 21. We're going to the casino after class, all right? Yeah. So you have the two probabilities of the individual events, right? Event A is the probability of getting five on one die, and event B is you getting five on the other die. So if you want to know what's the probability of you getting five on both, right? So that's 1 out of 36. Mhm. Yeah. Whenever you see the word and. Yeah. And is multiplying, right? Now, I know some people in here that's like, nah, I'm not in that multiplication game. I'll count out everything and then I'll do it, right? All right, bet. So here, let me show y'all sample space real quick. I'm gonna show y'all the sample space, all of the possibilities on the die. All right. Y'all need to know this for when we go to the casino, all right? Where the good casino at now? Is it Jersey still, or are we going out to Long Island? What we doing? You know? You haven't been to casino yet? Yeah, when you go to the casino too, like yo, like we be like youngest people there. Like, everybody there is like got like a good 10, 20 years on all of us. Like all of us in the room. You know, like, yeah. So look, this is the event you see circled in red. That's what I want to know, right? I want to know getting a five and a five on both of the die. But this right here, this whole table, this is all of the possibilities that you could roll with two dice. All of them, right? One and one, two and two. one and two, one and three, three and four, etc. Right? These are all the possibilities. And if you count them, how many pairs are there? It's 36 pairs. So that's why the probability of getting a five on one and a five on the other is 1 out of 36. All right. This is the reason why. Yeah. hmm Any questions on this? Anybody? Another one? Um, I got more. I got more. There's more to talk about. But yeah, this my favorite game in the casino. Craps, rolling the dice and all that. Do y'all know how that game works? The dice game in the casino, craps. Yeah. Huh? Yeah. Which one? Rayman? No, no. I didn't see Rayman. Yeah, yeah, I gotta watch that. Rush Hour 3 comes to mind. You remember Rush Hour 3? When he was there playing like that game that he was playing. That's what I'm talking about. You never seen Rush Hour 3? Yeah. One? Okay, okay. Yeah, yeah, yeah. Chris Tucker. Yeah. Part three, he was in a casino and he was just playing. He was winning like crazy. Like this one is for Mandela. All right, real quick, real quick. Let's jump into another example real quick. It's gonna be a little bit different, a little bit different. All right, but it's still important. All right. So multiplication rule for dependent events, right? Consider a collection of six balls, right, that are identical except in color, right? So there are three green balls, two blue balls, and one red ball. Compute the probability of drawing two green balls from the collection if the first ball is not replaced before the second ball is drawn. So imagine I have a bag or something, right? And these balls are inside, right? But I can't see into the bag. I can only stick my hand in and grab one out, right? So I'm asking the question, what's the probability of me putting my hand in, taking out a green ball, putting that on the side right here, and then putting my hand in again, and then taking out another green ball. So I want to know what's the probability of green and green. All right. So this is what I'm looking for, the probability of green and green. Now remember that general formula that I told y'all about that works for everything. That's what we're going to use right here. All right. So let's recap it real quick. So it's probability of A and B is equal to probability of A times probability of B given A. All right. So think of it like this, right? I want to know what's the probability of green times the probability of green given green. We could put in a fraction. So how many green balls are there? Let me help y'all out. Yeah. So how many green balls are there? Not five. Three, three green balls, right? So there's three. And how many balls in total? Six, right? So boom, right? So what I want is I want to take out one of them green balls. I have three of them that I could take, and there's six total balls, right? Now, how many green balls are left after I take out one? Two, right? There's two green balls left after I take out one, right? Now here's a little bit different of a question, right? How many balls are left in the bag since I took out one? Five, just like that. And then you just multiply straight like how you would, three times two, six, six times five, 30, and you're done. That's it. All right. Again, not really into simplifying and rounding and all of that stuff. I like big fractions like this. Just leave it at 6/30. All right. But yes, I know you could simplify it. Right? It'll be like 1/5 or something like that, but I don't care about that. Right? 6/30 tells you more information than 1/5. You know? If you ask me what is the sample space of this question, it's 30. If you ask me what's the chance of me getting green and green, there's 6 ways that I could get green and green. I get all that information from that one fraction. But if you tell me 1/5, you know, so for that reason, that's why I don't like simplifying. Just leave it as the big fraction and we're good to go. But is there any questions on this? Anybody? Good? This is what happened when you see the word and. It be like that. And. All right. So just like the previous question, just bear with me 1 second. I want to show you guys the sample space for this question. All right. So this is 3 green balls, 2 blue balls, 1 red ball, right? So one situation or whatever, right, is me taking out 2 balls from the bag, right? These are all the possibilities of me getting green and green, right? This is the one, two, three, four, five, the 6 events out of 30. And these are all of the 30 possibilities that could happen. All right. Questions? Good. All right. I believe this homework is posted also, so you guys will be able to practice when you go home as well. So the multiplication rules apply whenever we wish to determine the probability of 2 events happening together. To indicate together, we use the word and, right, between the events. But before you use a multiplication rule to compute the probability of A and B, you must determine if A and B are independent or dependent events, right? So here's your procedure, right? So how to use the multiplication rules. Step one, determine whether A and B are independent events. If the probability of A is equal to the probability of A given B, then the events are independent, right? Step two, if A and B are independent events, then the probability of A and B is equal to the probability of A times the probability of B. If A and B are any event, right, then the probability of A and B is equal to the probability of A times probability of B given A, or the probability of A and B, same answer, is equal to the probability of B times the probability of A given B. That's simple. Mhm. All right, so let's talk about what does conditional probability tell us? This is the A given B, B given A kind of thing, all right? So conditional probability of two events, A and B, tells us the probability that event A will happen under the assumption that event B has happened or is guaranteed to happen in the future. This probability is designated as probability of A given B, is read as probability of event A given event B. Note that the probability of A given B might be larger or smaller than the probability of A. All right. The probability that event B will happen under the assumption that event A has happened, right? This probability is designated as probability of B given A. Note that the probability of A given B and the probability of B given A are not necessarily equal. So if the probability of A given B is equal to the probability of A and the probability of B given A is equal to the probability of B, then these events A and B are independent. This means the occurrence of one of the events does not change the probability that the other event will occur. All right. So conditional probabilities enter into the calculations that two events A and B will both happen together. The probability of A and B is equal to the probability of A times probability of B given A. Also, the probability of A and B is equal to probability of B times probability of A given B. In the case that the events A and B are independent, then the formulas for the probability of A and B simplify to be just probability of A times probability of B. If we know the values of probability of A and B and the probability of B, then we calculate the value of the probability of A given B as probability of A given B is equal to probability of A and B over the probability of B, assuming that the probability of B is not equal to zero. Right? That's key. All right. Mm-hmm. I got. Huh? Yeah. Just explaining it. The one thing I want you to take away from this is when you hear the word and, you multiply. Go ahead. The third option, don't worry about it. You hear the word and, you multiply. That's all you need to know. And for the third option, whatever comes after the given, that's what's gonna be in the denominator. Right? So you just divide the two numbers and you're good. That's it. All right. Low key on your homework, you don't even have to do it in the calculator. Like you could literally just take the number that they give you, click slash, and then write the other number in the bottom, click submit, and that's it. So you don't actually have to calculate nothing. You know? That's how I do it. Cause y'all know I don't know my timetables. I'm faking it up here. That's how I do it. Yeah. Hmm. Yeah. Yeah. So the multiplication rule for independent events extends to more than two independent events. For instance, if the probability of a single seed will germinate is 0.85, and you plant three seeds in the ground, the probability that they will all germinate, assuming that seed germination is independent, is the probability of first germinating, second germinates, third germinates. You multiply your three probabilities together, and you get the likelihood that all three of them will germinate, which is 0.614. Right? Just to show you that this could be expanded. All right. And it doesn't just stop with two, it could go on for infinity. Right? All right. Let's get to your question now. Because this was just the tip of the iceberg. Right? This was the easy part, multiplication. Let's get to the hard part. Addition. Oh my God. That's the hard part right there. So, another way to combine events is to consider the probability of one event or another occurring. What's the key word there? Or, right. Good job. All right. For instance, if a sports car saleswoman gets an extra bonus if she sells a convertible or a car with leather upholstery, right? She is interested in the probability that she will buy a car that is a convertible or that has leather upholstery. Of course, if you bought a convertible with leather upholstery, that would be fine as well, right? So pictorically, right? I'm going to show you guys this picture, right? So in this figure, it represents the outcome of satisfying the or condition. Notice that the condition A or B is satisfied by any of the one following. Any occurrence of A occurs, any outcome of B occurs, or any outcome of both of them occurs, right? So it is important to distinguish between the or combination and the and combination because we apply different rules to compute the probabilities. All right. So let me show you this picture real quick so you guys can see. Just bear with me 1 second. All right. So these circles and this square thing right here, this is called a Venn diagram, right? A Venn diagram. You know what? In the next announcement, I might even put up a little comedy about Venn diagrams, right? I found a guy online who does comedy about Venn diagrams, believe it or not, right? Anyway, right? For what we just spoke about before, the and, notice where that occurs, right? And is, means together, it means union, right? So, I'm sorry, intersection, it means intersection, right? Think of and as a marriage, right? Both events have to occur together. But in or, right, this is the or situation right here, right? This is and. Anything could happen. Just A could happen, just B could happen, or both of them could happen, right? And that satisfies the condition, all right? Picture this, all right? Imagine back when you was real little, right? Like age 6 or 8 or something like that, right? And then let's say your parents came to you and was like, "Yo, you want cookies or you want ice cream?" Right? You know, the first thing coming to your head is both, right? So that's kind of like this situation here. I'm telling you, both is okay. You could have one, you could have the other, or you could have both. That's or, right? All three in one. Huh? Say it again? That's or for both. Yeah, for both. Yeah. So you could have one, the other, or both. All right. Let's look at an example real quick. I need to grab a picture. All right, just bear with me 1 second. I'm gonna read it out in a second. Just let me just grab this picture real quick so it can make a little sense. Okay. All right, let's get into it, right? So, probability of events combined with or. Consider an introductory statistics class with 31 students. The students range from freshmen through seniors, right? Grade one, oh, grade what? 13, 14, 15, 16, right? College, right? Freshmen through seniors, right? Some students are male, some are female, right? So here is a diagram to represent the students here, right? So the green students, those are freshmen, the blues are sophomores, the I guess that's orange is juniors, and the pinks are seniors, right? M stands for male, F stands for female, right? This is the breakdown of everybody there. All right. Let's go down to a question. Suppose we select one student at random from the class. Find the probability that that student is either a freshman or a sophomore, right? So they want to know what's the probability of freshman or sophomore, right? All right. So let's do it. How many people are freshmen? Hmm? Huh? Yeah. But how many freshmen are there in total? 15. All right. And then how many students are there in total? Right, we said it was 31, right? We said we're doing addition rules, right? Bam. Let me ask you another question. How many students are sophomores? It's a little bit harder. Okay. All right, now this is the hard part. You got to add those two together. All right. What's 15 plus 8? Y'all can use your calculators. I don't know the answer either. 23? All right. You're not saying that because that's the name of this class, right? Okay, good, good, good. All right. Yes. Good. Mhm. So that's it in a nutshell. Freshman or sophomore. Yes. And that's it. So we did this. This is good. Again, I'm happy with the 23 over 31. I'm not asking for the sun, the moon, the stars. You don't got to divide it and give me the decimal and all that. 23 over 31. We're cool. All right. That's that. How you did what? Oh, no, no, no. Those are the F and the M is female and male. Yeah, yeah, see. F for female, M for male. Yeah. Yeah, that was kind of funny. All right, here's another question. Uh-huh. Mm-hmm.
Have you seen the question plus, the probability that it will be female? It's not gonna work, right?
It does work. You tell me how many females are there? Not change it. You should just starts with a C. How'd you get that? You counted, right? That's it. Just count them. That's it. 17 over what?
39.
There you go. That's it. All right. It's that simple. All right, let's look at this part right here, right? So notice that we can simply add the probability of freshman to the probability of sophomore to find the probability that a student selected at random will be either a freshman or a sophomore. No student can be both a freshman and a sophomore at the same time, right? That don't make sense. It's nonsense. All right. Anytime two things don't make sense and they can't occur together, it's zero. All right. It's zero. Just like I don't even want to go here in 2026, but I'm going to go here for the sake of math, right? If we said for this question, what's the probability of male or female? All right. You could calculate the males, you can calculate the females, right? There's no such thing as male and female, right? At the same time. All right. In terms of math, I'm not talking biology here. I should edit that out the video. All right. Anyway, select one student at random from the class. What is the probability that the student is either a male or a sophomore? All right. A little bit different now. A little bit different. I'm going to erase this right here. Make it a little bit easier for us. All right. So we want to know what's the probability of a male or a sophomore. So let me ask you this. What's the probability of male plus the probability of sophomore? So for male, you said 14. So let me see. This is 3, 6, 9, 10, 11, 12, 13, 14. Okay, I agree. 14 over 31 plus, right? So that was, you just added up all of them, right? Now, what's the probability of sophomore? 8 over what? Over 31, right? So you just added up all of these people right here. All right. But I want you to notice something, all right? Y'all see them 5 males in the middle? They got counted twice. They got counted for male and they got counted for sophomore, right? So that means that this answer right here is wrong, right? I counted them twice. So what should I do? How can I fix this? Subtract it, right? Just subtract them people out, right? How many of them was there again? 5, right? Boom. So that's it right there, right? That would be subtracting out the, whoops, subtracting out the probability of the males and the sophomores. All right. Let's do the math on this. What y'all get? What's 14 plus 8 minus 5? Say it again. 17 over what? Perfect. That's it. All right. Questions on this? Anybody? This is the hard question right here. So we good? All right. Once again, you don't need to divide that out or give me no decimal, nothing like that. Perfectly fine with 17 over 31. All right. If it can be simplified, you don't need to simplify it. All right. Let's continue, all right? So we say events A and B are mutually exclusive or disjoint. It's another vocabulary word for today, right? If they cannot occur together. This means that the probability of A and B have no outcomes in common. Or put another way, the probability of A and B is equal to 0. So two events are mutually exclusive or disjoint if they cannot occur together. In particular, events A and B are mutually exclusive if the probability of A and B is equal to 0. Anytime you're doing this question and you hear some nonsense, right? Like, what's a good nonsense? Like you're a junior and you're a freshman at the same time. Anytime you hear some nonsense like that, right? The probability is 0. Those events are mutually exclusive or disjoint. Okay. All right. So the addition rule for mutually exclusive events A and B. So the probability of A or B is equal to the probability of A plus the probability of B. If the events are not mutually exclusive, we must use the more general formula, which is the general addition rule for any events A and B. For the general addition rule for any events A and B, right? So if you had to memorize one of these formulas, memorize this one, the general addition rule for any events A and B. All right. This is on your formula sheet. All right. Also, if you ever in a question that has or, you don't know what to do, use this formula. It works for every single or question. All right. Every single or question. All right. Let's recap. So probability of A or B is equal to probability of A plus probability of B minus probability of A and B. You may ask which formula should I use? The answer is use formula 7 only if you know that A and B are mutually exclusive, i.e. they cannot occur together. If you do not know whether A and B are mutually exclusive, then use formula 8. Formula 8 is valid either way, right? Notice that when A and B are mutually exclusive, that the probability of A and B is equal to 0. So formula 8 reduces to formula 7 anyway. All right. This is the sauce right here. I'll give you a little procedure. All right. So how to use the addition rules. First, determine whether A and B are mutually exclusive events. If the probability of A and B is equal to 0, then the events are mutually exclusive. If A and B are mutually exclusive events, then the probability of A or B is equal to the probability of A plus the probability of B. If A and B are any events, then the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. All right. Keyword there, any and or. All right. That's why we like that last formula. Oh, shoot. Here we go. This is my other game right here. Yeah. Which other math class y'all be talking about games and gambling? All right. It's the best math class right here. All right. So, what does the fact that two events are mutually exclusive tell us, right? If two events A and B are mutually exclusive, then we know the occurrence of one of the events means the other event will not happen. In terms of calculations, this tells us that the probability of A and B is equal to 0 for mutually exclusive events. The probability of A or B is equal to the probability of A plus the probability of B for mutually exclusive events. The probability of A given B is equal to 0, and the probability of B given A is equal to 0 for mutually exclusive events. That is, if event B occurs, then event A will not occur, and vice versa. All right. This will save you a lot of time on your homework if you remember this part. All right. The addition rule for mutually exclusive events can be extended to apply to the situation in which we have more than two events, all of which are mutually exclusive to all the other events. All right. For example, let's talk about mutually exclusive events. Laura is playing Monopoly. That's my game right there. That's my game. On her next move, she needs to throw a sum bigger than 8 on the two dice in order to land on her own property and pass go. She blessed, right? What is the probability that Laura will roll a sum bigger than 8? I already know what this is, man. She looking at Park Avenue and somebody got a house or hotel on that joint, and if she land on it, she's done, right? Well, she got them little brown, what you call it, places right there, them cheap places, and she got hotels on there. That's what she's trying to land on. I already know the game. I already know the game. All right. So, what is the probability that Laura will roll a sum that is bigger than eight? Let's talk about this, right? So, probability of sum bigger than eight. All right. Y'all gonna have to help me out. All right. Which numbers are bigger than eight? Hmm? All right. So we got the probability of nine plus the probability of 10 plus what else? Plus 11 plus 12. Can I write 13? Why? You're right. Why can't I write 13? Exactly. Right? So remember when we rolled the dice, right? It has six sides, right? The biggest side on the dice is six. So six and six adds up to 12. So I can't get 13, right? So the probability of me getting bigger than eight would be 9, 10, 11, and 12. All right. How many sums are there for nine? Like, how many ways can I get nine on the die? One, two. I ain't gonna hold you. I don't know. But I have a way of figuring it out, though. Right? Huh? That is what I meant, but I just don't know I just don't know if you're right. You probably are right, though. But here's how I figure it out. So I want the sum to be nine, right? I just count down, right? So start with one. So one and eight, that doesn't work because there's no side of the die that's equal to eight. How about two and seven? There's no side of the die that's seven. So three and six, right? And then what I do is I add one to this side and I take away one from this side, right? So three plus one is what? Four, right? And six minus one is five. Yeah. But I need all the possibilities. So keep going. What's going to come after four and five? Five and four. And then what's the last one? Six and three, right? So there are one, two, three, four possibilities to get nine out of, no, when I'm rolling two dice, what's the total cost? Not six, two dice. Not 12. No, six sides on each times 36, right? The total possibilities, right? How about 10? Think the same way, all right? One and nine, that's not possible. Two and eight, that's not possible. Three and seven, not possible, all right? Four and six, that works. What comes after four and six? Five and five. And what comes after that? Six and four. Very good. So there are one, two, three possibilities, three ways that I can get a sum of 10, right? So plus three out of 36. What about 11? How many ways can I get 11? Okay, so five and six, and then six and five, right? Right, so two, out of 36, right? How many ways can I get 12? One, right? That's six and six, right? After this, just add them up and you're good to go, right? So 4 plus 3 plus 2 plus 1. What's that? Like 10 out of 36? Something like that. And that's my answer. Questions on this? We play Monopoly later? Mhm. I'm okay. I mean, I'll be whooping my computer's butt though. Yeah. Yeah. Did he? That's fire. There was this old professor, like PhD in math, and he started an investment firm, like investment company. Yeah, he made mad money too using math. Yeah, yeah. I know math. There's no reason to. Gambling is like if you don't know the outcome or the possibility, so you're just putting down money and whatever happens, happens, you know? Yeah. That will give me an outcome that's a winning. Yeah. This is why I like crafts because I can win at that, you know? Why I like blackjack, all right? It's a card game. Yeah. You count the cards and you want to get a sum that's equal to 21. Yeah. Yeah. I play on my phone on an app without money. Solitaire is fun too. Solitaire is fun too. All right. So I hate when I got this pop-up right here, man. Coming out of nowhere. I haven't seen it. I would like to see it though.
That they go to the
Mm.
casino, fix them, his parents died, they had money, he had a long lost brother, you know, and he was in a fine something.
Yeah.
And he goes to get him and realize that he's good with numbers, the artistic.
Oh, interesting. Nah, I would like to though. That sounds fun.
When he get.
Yeah. And it just flips it. Yeah. Yeah.
When they think they're not something bad.
Wow. I'm gonna look for that movie tonight. Rain Man, like RAIN, like RAIN, Rain.
Yeah.
Rain Man. Okay, I'm gonna look at that. Yeah, I like to watch movies. So Fanta, that's her thing too. Loves movies. Fanta Marie. All right, next thing, right? Further examples using contingency tables. So most of us have been asked to participate in a survey. Schools, retail stores, news media, and government offices all conduct surveys, right? There are many types of surveys, and it is not our intention to give a general discussion of this topic. Let's study a very popular method called a simple tally survey. All right. Such a survey consists of questions to which the responses can be recorded in a rows and columns of a table called a contingency table. All right, contingency table. So these questions are appropriate to the information you want and are designed to cover the entire population of interest. In addition, the questions should be designed so that you can partition the sample space of responses into distinct, that is, mutually exclusive events or sectors, right? If the survey includes responses from a reasonably large random sample, then the results should be representative of your population. In this case, we can estimate simple probabilities, conditional probabilities, and the probabilities of some combinations of events directly from the results of the survey. All right. So, for example, this is going to be good. I'm not even going to lie to you. This is going to be the easiest question on your exam. The easiest question. There ain't no math in this question or nothing. You're just going to look at it. You're just going to tell me the answer, and that's it. All right. Very, very easy. Don't none of you get this question wrong. All right. Nobody's allowed to get this question wrong. All right. Here we go. So let's look at this survey. At Hopewell Electronics, all 140 employees, how many employees? 140, right? Were asked about their political affiliations. The employees were grouped by type of work as executives or production workers, right? The results with the rows and columns are shown right here. So let's take a look at this, right? So these are the employee types and their political affiliations. Here's for the executives, right? These five executives here, they're executives and they're Democrats at the same time. You know, these are for the Republican, the independents. When you go straight across, this is what's called a row total. The row total is just the sum of all of the executives, right? Same thing with a production worker going straight across. You have the all of the production workers, right? Going down, you can find all of the political affiliations. Like these are all the Democrats right here, 68. That's a column total, right? Column total. For the Republicans, just going straight down, you can see all of the Republicans, there's 55 of them. That's the column total, right? You just add up the numbers right above, right? In the lower right-hand corner, this is what's called the grand total, right? This is the sum of everything. This is how many workers there are in a survey from the get-go, right? All right. Anyway, suppose an employee is selected at random from the 140 Hopewell employees. Let us use the following notation to represent the different events of choosing E for an executive, PW for production worker, D for Democrat, R for Republican, I for independent. Here's the question. What's the probability of a Democrat? Write it right here. What's the probability of a Democrat? How many people are Democrats in this table? 68. Over. How many people are in the table? 140. I'm done. That's it. All right. What's the probability of you being an executive? How many executives are there? 48, right? There's 48 executives going straight across. How many people are in the table? Huh? 140. I'm done. That's it. Any questions on this? Contingency table. Contingency table. I'm getting to that. Right. But individually, yeah. Yeah. No, that's separate. If it was both, it would be like probability of Democrat and executive in the same parentheses. Yeah, but I'm getting to that. Like they'd be in the parentheses together. Yeah, I'm getting to that though. But just in general, like if I ask you probability of production worker, what you gonna tell me? Yeah, PW. That's it. All right. If I ask you what's the probability of independent, what you gonna tell me? No, not 9. 17 over what? That's it. All right. So we good. Mhm. Get it? All right. Hold on. I'm not looking at the screen. Executives know 48. Um, was a Republican? I asked you. Oh, independent. No, you got it right. 17. Yeah. Production worker, I think that's what you got wrong. So you see how that's a roll total 92 over. Yeah. All right, new question. Make it a little bit bigger so you guys can see, right? What's the probability of a Democrat given executive? It's the probability of a Democrat given executive. 5,
No, five,
not 68.
5048.
5 over 48. That's good. A little bit. A little bit, little bit. All right. So, what's the question is probability of Democrat given executive, right? So how many Democrats are executives? Mm-mm. How many Democrats are executives
Are accepted.
at the same time? That's the 5,
Okay.
right?
The number is five.
Yeah.
Okay.
But here's my question though, right? You were right. It's 5 over 48. How'd you get the 48?
The 48. That is done.
Mm-hmm.
For the total number of executives.
Yes.
Democrats, five, and the total number of executives.
Yes. All right. I was looking for a little bit more of a simpler answer. It was something I said earlier in the class. All right. Whatever comes after the given is your exactly. All right. So what came after the slash? Executive. And how many executives are there? 48. That's it. Right? Yeah. All right, same thing. Same thing, same thing. All right, new question. Let me see. Oh, baby. New question. Are the events Democrat and executive independent? Are the events Democrat and executive independent? Or is it are the events Democrat, right, and executive independent? It's a yes or no answer. Are the events Democrat and executive, are they independent? Yes or no?
No,
Why?
because there's five executives that are Democrats.
Yes.
There's one.
Yes, that's the reason right there. All right. Yeah. So I'm asking you if executive and Democrat are independent, right? Remember, independence means that if one occurs, it doesn't affect the other event from occurring, right? Meaning that there cannot be an event where they occur at the same time. But there are 5 people here who are Democrats and executives at the same time, right? Because of that, they're not independent, they're dependent, right? That would be independent. Independent. Yeah. Dependent. That's this. Yeah. Yeah. Disjoint. Yeah. That's this. No. Wait, let me think about that. It doesn't mean disjoint. Just that it can't occur together. Let me think about that and get back to you on that. Because I don't want to give you the wrong information about that. But just know that no, these are not independent. Because, right? Democratic and executive exist together. Very simple, like that. But I will get back to your question at the end, though. All right, I got two more questions, and I got 2 minutes. Real quick, real quick. What's the probability of Democrat and executive at the same time? Just shout it out. No. What is it? Five over. No. Five over 140. That's a. Uh-huh.
So let's say, you go back up.
Uh-huh.
So the person was Democrat and executive, right?
Uh-huh.
Johnstown becomes zero, it's like Democrat.
So how many Democrats are executives at the same time?
Yeah, I see that, but
Yeah.
let's say it's like it couldn't be that, and you can't be Democrat or Republican, so you can't say like, that's when it becomes zero, right? So if you say like, how many executives are Democrat and Republican? Like, how would that be like one that you can't do?
So like if I asked you what's the probability of Democrat and Republican at the same time, right? That can't happen. Yeah. It will look like nonsense.
Okay.
Like I'm sorry. You want to see the table? Yeah. When you see that type of question, like I promise you it's gonna look like complete nonsense, you know? Yeah. Like if I asked you what's the probability of a person being a production worker and an executive at the same time, that'd be zero, right? That doesn't make sense. Yeah.
They can't have.
Right.
I mean, technically they could, but.
But not in the same company.
Yeah.
Yeah. All right. Real quick. Oh shoot. It flipped upside down on me. All right. What's the probability of a Democrat or an executive? All right. Going back to our formula, you know that's going to be what? The probability of Democrat plus the probability of executive minus the probability of Democrat and executive, right? So how many Democrats are there? Over? Perfect, right? So we just added up these well, not those numbers, but we added up these numbers right here, right? Okay, so that's 68 over the 140, right? Plus, how many executives are there? Executives, 48, right? Over. Good, right? So we just added up these numbers right here, right? So That's the 48 over 140. Minus now, how many people are Democrat and executive at the same time? Five, right? That's the people that I counted twice, right? So that's the 5 over 140. A little bit of math, boom, boom, boom. What is that? That's three, call that 70. I don't know. What y'all got? What's 120? What you got?
Plus.
Well, 111, something like that. What y'all got? Y'all can use our calculators, you know. What you got?
116.
116,
No. Yeah. Yeah.
which is 111.
But
Yeah,
116 minus 5.
yeah. So 111 over 140. Okay. That's it in a nutshell. Hmm. Have a little bit more, but we'll cover that tomorrow. All right. If y'all didn't have a chance to sign the attendance sheet yet, come up and sign. All right. The 140 is a grand total. It's everything. Oh shoot. Yeah, yeah, we good. We good. All right. All right. I will see y'all tomorrow. Okay. Can I take this down? Yeah. Appreciate y'all. Thank you.